In section 5.3, we will be looking at greatest common factors and how to factor by grouping. Now, so far in this chapter, we've covered how to add, subtract, and to multiply polynomials together. We are going to save the concept of dividing polynomials for a later chapter when we come back and cover a whole group of functions whose very definition are the division of two polynomials. So what we're going to jump ahead now to is the next essential element that we need to solving equations that involve polynomials, and it's factoring. And factoring is actually a kind of division. If you think of division as the opposite of multiplication, in the sense that division is trying to find what times the divisor gives me the dividend, then factoring is very similar, because we're going to take a polynomial and try to break it into two simpler polynomials that multiply together to give me the original polynomial. So factoring is like a division, but it's a very key step in the solution or solving of polynomial equations. So we begin with our first type of factoring here in section 5.3. The outline for section 5.3 is as follows. We're going to start by talking about how to factor out the greatest common factor of a polynomial. Then we're going to look at the special rule that we have to remember whenever the first coefficient is negative. So how we factor out the greatest common factor with a negative coefficient. And then last of all, we're going to talk about factoring by grouping. Let's start by talking about what we mean by the greatest common factor. So by definition, if you have a given list of terms, the greatest common factor is the expression of the highest possible degree that divides every term or each term in that list, or each term of the polynomial. So for example, if this is your if this is your polynomial and you're asked to find the greatest common factor, what we're looking for is the largest number that divides into both 21 and 28 and the largest variable expression that divides into x squared and x. Another way of saying that is the largest I can get from to these two expressions by multiplying by some other expression. Now, let me go ahead and fill in the note down here, because that will help us figure out how we find the GCF. For coefficients, the GCF is the largest number that divides into all of the coefficients. Now, for variables, the GCF is the variable to the smallest power that appears. Now start with the first one. What's the largest number that goes into 21 and 28? The largest number that goes into both of those is 7. So that's the coefficient of the GCF. Nothing bigger divides evenly into 21 and 28. Now x is in both of these. The GCF is going to be the variable with the smallest power that appears. Now we've got a squared and a first power, so that means to the first power is the smallest power. Now, why is this the smallest power and not the largest power? Well, the most they have in common is just 1, right? Because they don't have two x's in common, because this one only has one x. So the most that they have in common that makes it a common factor is the smallest power that appears. So that's the GCF for that expression. Now what we're going to do is we're going to take polynomials like this and pull out or factor out the greatest common factor. So in order to factor that monomial out from a polynomial, we first have to determine the greatest common factor, or GCF, for all the terms in the polynomial. Then we're going to express each term as a product of the GCF and the other whatever's left over. And then we're going to use the distributive property to factor out the greatest common factor. Let us go through those steps for this particular example. Let's start off by finding the greatest common factor. So we're looking at the numbers first of all and say, what's the biggest thing that divides into 49, 70, and 35? And I see that they all share a factor of 7. right? And nothing larger divides into each one of those. So the GCF contains the number 7. Now look at the variable x. What's the smallest power that you see? We have a 4, a 3, and a 4. So the smallest power is cubed. For y, again, the smallest power that we see is from 3, 5, and 4 is a 3. And for the z, the smallest power we see from 5, 4, and 3 is 3. So your GCF is 7x cubed, y cubed, z cubed. Okay? Now, what you want to do is take every one of these expressions that are the terms of the original polynomial and write it as 7x cubed, y cubed, z cubed times something else that would equal 49x to the 4th, y cubed, z to the 5th. So 7 times what gives me 49? The answer is 7. X cubed times what gives me x to the 4th? Well, that needs one more x. Y cubed times what gives me y cubed? Well, 1, so I don't need to include any y's. And z cubed times what gives me z to the 5th? Well, because we add exponents when we multiply like bases, it's 2, z squared. Right? This is the same thing as the first term in the polynomial. Now do that again. 7x cubed, y cubed, z cubed. What do I have to multiply this by to get to 70? X cubed, y to the 5th, z to the 4th. To get from 7 to 70, I have to multiply by 10. By the way, if I want to be particular about this, I'm going to put a plus sign between each one of these. And since it's negative 70, I need a negative 10 to pull out, right? I think that's the easiest way to see this. Now, x cubed, I've got x cubed. To get to y to the 5th, I need 2 more y's. To get to z to the 4th, I need 1 more z, so it's y squared z. And then plus a 7x cubed, y cubed, z cubed, times what's left over. I need to get from 7 to 35, I've got to multiply by 5. I need 1 more x and 1 more y to get x to the 4th, y to the 4th, z cubed. Now what I'm going to do is I'm going to pull the common factor out front using the distributive property. Write it as 7x cubed, y cubed, z cubed times everything that was left over. I had a 7xz squared, I had a minus 10y squared z, and I had a plus 5xy. Because the distributive property says that this is the same thing as multiplying the monomial times every term in the polynomial, which is exactly what I've done. I've just done it in reverse. Now that is factoring out the monomial from the polynomial, pulling out the greatest common factor. Notice, by the way, this has no GCF left. If you did this right, the remaining polynomial will not have a common factor. There's nothing in common from these three terms. All right, next thing. Same process on the next example, but there's a rule we're going to adopt from this point on. And anytime we see that the leading term of a polynomial is negative, we're going to factor it out, meaning factor out the negative sign. So in this case, whenever I say find the GCF, I will look and say, what do 5, 50, and 10 have in common? The largest number that goes into all three of those is 5, but because the leading term is negative, I'm going to put a negative in my GCF. Now what's the power of x that's the smallest? We have a 3, a 2, and a 1, so to the first power. There is my GCF, is negative 5. Now I'm going to write each one of these as negative 5x times something. Now to get to negative 5x cubed, I don't need another number, but I do need an x squared, plus negative 5x. Okay, what do I need to multiply negative 5x by to get to 50x squared? Well, to get to a positive 50, I need a negative 10. Negative 5 times negative 10 will give me a positive 50. And I need one more x. All right, to get to minus 10x, I just need a 2. And so pull out the negative 5x, and what's left behind? I have the x squared, a minus 10x, and a plus 2. That remaining trinomial has no common factors, so I have factored out the monomial, or the greatest common factor. Now we see something a little bit different on this example. When we look at the terms of this polynomial, we see that this minus sign right here is separating this term from this term, and they both have in common the x plus y. Correct? So the GCF that these have in common is a binomial, which is perfectly possible in these types of problems. That the thing that they have in common is not just a single monomial, but maybe even a binomial. Now, if I were to factor out that GCF, I need to ask myself what's left behind when I pull it out. The first term was 7x times the GCF, so it's going to have a 7x in it. The second term was a negative, which is always understood to be a negative 1, so minus 1. This expression is the same as this one. We factored out the x plus y. So let's talk about how we factor by grouping. First thing you're going to do if you want to factor by grouping is you are going to group terms together that have a common factor. Usually it's going to be two groups of 2, but sometimes you may have to rearrange that. Sometimes it's possible to have different sized groups, but most of the time in our grouping, the first thing to try is to group them into pairs. Once you've done that, factor out the greatest common factor from each group. Then, if it works out that the result from number 2 has a common binomial, like we just saw in our last example, then we're going to factor it out if it exists. Notice we could do that with this example right here. Let's try this out. Let's group them this way. Let's put these two together in a group and these two together in a group. Alright, so what is the GCF for the first two terms, just that pair? Well, it's going to have a 3 in it. It's going to have an a squared, but it doesn't have an x in it because they don't share an x and they don't share a y. So that's the GCF. Now pull that out. We'll do this all in one step. What are we left behind with? If I remove the 3a squared from the first one, I'm left with just an x. And if I remove the 3a squared here, that is 3a squared times what gives me 6a squared y, I'm going to have a plus 2y. Alright? Now, what's the GCF of these two? Well, since the first one's negative, it's going to have a negative in it. And the largest number that comes out of both of those is 2, and there's a b in common. So what happens when I pull out a negative 2b from the first term? I end up with a positive x. And when I pull out a negative 2b from negative 4by, that is, what is it that I multiply times negative 2b to get negative 4by? The answer is positive 2y. Now look at the result. This plus sign separates two terms that have in common this binomial right here. So for step 3, we will factor out that binomial and write down what's left behind. I had a 3a squared and plus a negative 2b or minus 2b. We have factored that polynomial by grouping. Now you may be asking yourself as we go through this, why in the world are we factoring at all? Why is that important? Let me give you one example where factoring can help us answer a question that's a very common misconception. But also, let me say that we are going towards a goal, and that goal is solving equations that have polynomials in them. It turns out that the technique that works for solving polynomial equations is to use factoring. And so we're going to use factoring, and we're going to use it a lot, especially as we solve equations here. But those of you that are going to take college algebra after this course is over, you will use a lot of factoring as soon as you start chapter 6 out of this same textbook in that course. Let's look at this example. Your local electronics store is having an end-of-year sale. The price on a large screen television had been reduced by 30%, but now the sale price is going to be reduced by another 30%. If X is the original sales price, then the new sale price can be represented in the following way. Now, let me point out where this formula comes from. Remember that if you take something that has value X and you want to reduce it by 30%, you will subtract 0.3 of X, or 0.3 times X from it, right? Well, they're saying reduce this amount by 30% of this amount. They're going to take 30% off the new sales price. So what they did is they took the X minus 0.03 or 0.3X and subtracted 0.3 times X minus 0.3X. That's the sale price discounted another 30%. Now, your intuition may tell you that if you take 30% off twice, it's like taking 60% off. But that's if you take 30% off the original amount twice. But we're not doing that. We're taking 30% off something that's already had 30% taken off. Now, what we want to do is we want to simplify this expression. I'm going to suggest we do it using factoring by grouping. Factor out the X minus 0.03X from each term and see what you get. Okay, so they both have the X minus 0.3X. What's left behind when you pull it out? Well, there's an understood 1 right there. So I'm left with a 1. And there's a 0.3 here subtracted, so minus 0.3. But what is 1 minus 0.3? That's just 0.7, right? Now notice what you have here. You have 1x minus 0.3x. Those are like terms, right? You just subtract their coefficient. You end up with 0.7x times 0.7, which gives me 0.49x. That's the simplified expression for the final sales price. Now, if we use the simplified expression from Part A, we can answer the following question. With a 30% reduction followed by another 30%, is the TV selling at 40% of its original price? 40% would be 0.4 of X. Is that what it's selling for? And it's not, right? No. What is it selling for? What is the percentage we have here? It's selling at 49%. And that all goes back to the fact that you are, got a percent sign there, that you are taking the 30% off from the sales price that you already took 30% off of. Right? So that's the final answer there. All right, that's the end of the factoring by grouping section 5.3.